Today's lecture is going to cover quality assurance. Quality assurance includes activities that ensure consistently high-quality images and services. We can use the FOCUS or PDCA process, which means plan, do, check, act. Step 1, we will find the problem. Step 2, we will organize a team. Step 3, clarify the problem. Step 4, understand problem and potential causes. Step 5 is implementing the plan. Step 6 is full implementation. Step 7 is checking the results. And step 8 is to continue to act to look for improvements. Quality assurance evaluates activities, equipment maintenance, performance of procedures, interpretation, staff development, and supply lines. Quality control monitors technical equipment to maintain quality standards. For external beam evaluation, dosimeters measure primary beam output, and this should be done semi-annually. For focal spot size estimation, this ensures proper image detail. There are 3 types: line pair resolution test tools, star test patterns, and pinhole cameras. Line pair resolution and star test patterns are measured by creating a pattern on an image. Pinhole cameras create an image of the effective focal spot on an image. Focal spots between 0.8 millimeters and 1.5 millimeters may be 40% larger than nominal. Focal spots larger than 1.5 millimeters may be 30% larger than nominal. Filtration affects image quality and radiation protection by reducing the low energy photons in the primary beam. This is measured by dosimetry to detect quality of aluminum filtration needed to reduce the beam intensity to half of the original value, also known as half-value layer. Additional filtration can be added to the tube housing if needed. Recommendations and requirements vary depending on the kVp used. The alignment of the central ray, collimator, and bucky are critical to radiation protection. Overcollimation and excessive amounts of irradiated tissue can degrade image quality and increase patient exposure. 2% SID error is allowed between primary beam size and light field size. The centering mark should be within 1% of the light field central ray, and positive beam limitation should not permit beam size greater than the cassette or image receptor size. Distance and centering indicators ensure that distances, techniques, and detents are accurate. Distance indicators should be plus or minus 10%, and centering indicators should be plus or minus 2%. Angles should be within plus or minus 1%. kVp settings drift over time due to tube aging. This affects scale of contrast, density, and quality of the beam. Generator recalibration is needed if the settings drift beyond plus or minus 5 kVp. Exposure time can also drift due to tube aging. The spinning top test can be used to measure single-phase machines, and motorized synchronous tops can be used to measure 3-phase. Computerized dosimeters provide more accurate readings and are less time-consuming and easier to use. Exposure time settings should be within plus or minus 5%. Exposure cannot be predicted unless MA is accurate. This is measured after exposure time and kVp accuracy has been tested. MA stations should be within plus or minus 10% of each other. Other sources recommend maintaining the entire generator within plus or minus 10%. Generators must be capable of repeating exposures accurately, also known as exposure reproducibility. Reproducibility should be within plus or minus 5%. Specialized equipment such as fluoro, tomo, and AEC require additional testing. Fluoroscopy uses AEC. Exposure reproducibility should be within plus or minus 0.1. The exposure rate should not exceed 5 roentgens per minute. The field size or beam alignment should not be capable of irradiating tissue outside of the image receptor area and should display within 1 centimeter of the edges. The source to skin dose limit should not be able to bring the tube closer than 15 inches for fixed fluoroscopic equipment or 12 inches for mobile equipment to the skin surface. Resolution is poorer than radiographic because the screen mesh test tool or resolution pattern test tool is used to evaluate detail. Image display systems, such as videos, are tested using a resolution test tool or fluoroscopic mesh tool. Automatic brightness control is tested by using a dosimeter that is used to test varying thicknesses of part in relation to exposure readout. For tomography, uniformity and completeness of motion lead mask with a pinhole. Section depth indicator accuracy is sharpness at the fulcrum level is necessity and can use a penetrometer or commercial test tools. Also test section thickness accuracy, which is dependent on exposure arc or angle, and the resolution test pattern at the fulcrum level is used to test resolution. For automatic exposure control, the exposure reproducibility has the same standards as for general radiographic systems. The ion chamber sensitivity test ensures that each chamber is equally sensitive. All chambers must respond to within plus or minus 10%. IR exposure variation control accuracy allows for sensitivity of chambers to be modified. The response capability, measured by the minimum response time, is within plus or minus 10% of the MR per mass. The backup timer verification is used to help protect the patient and tube from overexposure. Digital radiography detectors use the DQE or detective quantum efficiency, which measures the ratio of transfer efficiency to the detector as signal to noise and should be from 0 to 1. All image receptors should be inspected for wear and cleaned with proper cleaning solution periodically. Any image receptors that are warped or damaged should be discarded. Cleaning ensures image is free from artifacts caused by dust, foreign particles, hair, and smudges on the screens. For digital radiography detector systems, erasure should be performed daily. Inspections for cracks and surface markings should be performed semi-annually, and exposure tests should be performed semi-annually. For display monitors, spatial resolution and optical density must be evaluated on a regular basis. Spatial resolution is evaluated by using a SEMTI test tool. For PACS, there is a need to test the quality of the connection between the modality system, which involves either the CR, CT scanner, or MRI scanner, and the electronic medical record in the hospital information system and radiology information system. Repeat analysis is used to determine if technical or equipment issue by looking at cause for the repeat. Some areas may include motion, overexposure, underexposure, artifacts, or positioning. The total repeat rate is calculated as the number of repeats divided by the total number of images or exposures. It must be below the national average to comply with Joint Commission standards, and it should be between 3 and 10%. Troubleshooting allows to find causes of problems in order to find the correct solution. It can minimize the calls to service for routine basic problems. It is also used to find minor problems before they turn into more complex issues and can void service contracts if acting outside of the realm of experience. In summary, quality assurance is a process which evaluates all aspects of the imaging department. Quality control is a process which only evaluates the equipment. These duties may be assigned to staff members after demonstrating competency and accuracy. Preventative maintenance is typically performed by vendor service personnel and physicists.